Ever wondered how engineers ensure self-driving cars avoid collisions, or how medical devices prevent life-threatening errors? The answer lies in a mathematical challenge as old as probability itself, finding rare, critical events in vast, complex data. Today, we're diving into a breakthrough that's reshaping how we tackle this problem. MPPCA, a low-rank probabilistic model that outperforms traditional methods in high-dimensional safety-critical systems. Let's start with the basics. Imagine you're testing a plane's autopilot system. You can't simulate every possible flight scenario. There are billions of variables. Instead, you focus on the most critical ones, like sensor failures or extreme weather. This is the essence of importance sampling. Instead of randomly guessing, you strategically target the data points most likely to reveal failures. But here's the catch. When systems have thousands of variables, like a self-driving car's LiDAR, radar, and cameras, traditional methods fail. Why? Because they rely on Gaussian Mixture Models, GMMs, which assume data follows a normal distribution. But in high-dimensional spaces, GMMs hit a wall. They're covariance matrices, which describe how variables interact, become unstable like a wobbly table in an earthquake. They're computationally expensive, memory-heavy, and prone to errors when dealing with rare events. Enter MPPCA, mixture of probabilistic principal component analyzers. Think of it as a smarter, streamlined version of GMMs. Instead of modeling every possible relationship in a high-dimensional space, MPPCA identifies the most important ones. It's like using a magnifying glass to zoom in on the key patterns while ignoring the noise. This reduces complexity without sacrificing accuracy. Here's how it works. MPPCA uses the expectation maximization, M, algorithm to iteratively refine its predictions. It starts by guessing the most likely failure scenarios, then adjusts those guesses based on new data. But here's the twist. Because failures are rare, it employs important sampling to focus on the right data points. Instead of treating all samples equally, it weights them based on their likelihood of leading to failure. This makes the process exponentially more efficient. To test this, researchers applied MPPCA to 3 real-world systems. 1. Branches, a mathematical model with 40-60 variables mimicking complex failure patterns. 2. Duffing Oscillator, a physics-based system modeling vibrations like a car's suspension. 3. F-16 fighter jet, a high-stakes example where the model simulated sensor errors to test collision avoidance. Compared to traditional GMMs, MPPCA delivered higher accuracy with fewer samples. For instance, in the branches dataset, it achieved 94.3% coverage of the data space with minimal error, minus 0.024, while GMMs struggled with instability. In the Duffing Oscillator, MPPCA's low-rank structure handled 200 dimensions without the computational overhead of full covariance matrices. Why does this matter? Safety-critical systems, like drones, medical devices, or space missions, rely on simulations to avoid disasters. By making these simulations faster and more reliable, MPPCA brings us closer to safer technology. So next time you see a self-driving car or a drone in the sky, remember, behind the scenes, models like MPPCA are working hard to keep things from going boom. Thanks for watching, stay curious, and let me know what you'd like to explore next. But here's a deeper question. How do we even measure if these models are good? That's where generative performance metrics come in, tools that evaluate how well AI captures real-world patterns, especially in high-dimensional dynamic systems. Think of it as a fitness test for AI. Does it generate diverse, realistic data, and how does it handle noise or unexpected changes? These metrics go beyond simple accuracy. They assess sample density, how closely generated data matches real-world patterns, and coverage, how broadly the model explores the data space. For example, a self-driving car's AI must not only navigate smoothly under normal conditions, but also handle sudden obstacles. In the study we discussed, researchers tested methods like CMPPCA and SysMPPCA against GMMs across datasets with varying complexity. The results: CMPPCA excelled in accuracy but missed some rare events, while SysMPPCA balanced coverage and diversity better in high-dimensional spaces. The F-16 GCAS dataset revealed similar trade-offs, highlighting the need for metrics that adapt to real-world unpredictability. So whether it's a drone avoiding a storm or a medical device detecting anomalies, these metrics are the unsung heroes ensuring AI systems are both powerful and trustworthy.